In this next lesson, what we're going to talk about is force and start going through Newton's laws of motion because they relate to this combination of both force and motion. So we need to start off by defining what exactly a force is. A force is a push or a pull that one body exerts on another. When this push or pull is exerted, it can cause the motion of an object to change. So in other words, it's going to be accelerating. Forces can cause a resting object to move, and acceleration can be caused by either changing the speed up and down or the change in direction. So when we measure force, we use something called a spring scale. And you often see these, and I'll show you a picture on the next slide of these at the grocery store. We will also be using them in the lab. Basically, how far the spring stretches depends on the mass of the object, so we can actually measure the force that object is exerting. The unit of force is a newton, and a newton is described as 1 kilogram accelerating at the rate of 1 meter per second squared. So here's the equivalency. 1 newton is abbreviated with a capital M, equals a kilogram times meters divided by seconds squared. Basically, what you just need to remember in this, in order for us to get force in newtons, we have to have our mass in kilograms and our acceleration has to be in meters per second squared. We represent force using arrows because force is a vector quantity, so direction does matter, just like displacement and just like velocity. This arrow is going to show our strength and our direction of the force. So what we can do is we can actually measure the length of that arrow because it's going to represent the strength, how strong that force is, or sometimes we refer to this as the magnitude. And you can see this here on the two different spring scales. So I have some apples in here and they are exerting a force that is downward and it has that magnitude. If I add more apples, the force is still going to be in the same direction, but it is a greater magnitude. Now, single forces are pretty easy to observe, but in many cases, forces that are acting upon an object are a little bit more complex. So oftentimes we have to combine forces. Just like with distance and displacement, if the direction of the force happens, the two forces happens in the same direction, all we do is we add together their magnitudes. Forces in the opposite direction subtract from each other. When we do this addition or subtraction of the magnitudes, we get a net force, which is the overall force that acts on an object. So based on this, we can actually describe things as forces as being balanced or unbalanced. And what we're going to do is we're going to take a look at balanced forces first and then look at unbalanced ones. When I have a balanced force, the forces that are placed on the object are equal in strength but opposite in direction. Their net force that they produce are zero because they have the same strength, same magnitude, but because they're in opposite directions, we subtract them and they cancel each other out. So this will create no change in the object's motion. So therefore the acceleration is zero and the object is at what we call equilibrium. Now there's two types of equilibrium that we can have. We can have static equilibrium, which is the first one we're going to look at, where the object is at rest. So for instance, let's take a look at the example here with a book on the table. I can have 20 newtons of the book pushing down, okay? That is the weight of the book and that is a force. But if it's sitting on a table, it's not moving, and that's because the table is providing 20 newtons of force in the opposite direction, and so those two forces cancel each other out, and the book doesn't move in either direction. Your chair does that when you sit in it, the floor does that when you stand on it. So these are equal forces in opposite directions. So my acceleration here is zero. Now in this case, the object is not moving. When we have something, though, called dynamic equilibrium, for instance here with the plane, okay, the force of the engine is pushing the plane this way, and the force from the air resistance is pushing back against the plane. In this case, our plane is not accelerating, it has a constant velocity. So again, our acceleration is 0 and our net force is 0 because these two forces, again, are equal in size but opposite in directions. Does not necessarily mean that the object is not moving, though. Now, the unbalanced forces, okay, this is when the two forces are placed and they are not equal in strength, but are in opposite directions. So the net force is going to equal the size of the larger minus the size of the smaller, and the net force will be something other than 0. What this is going to do is it's going to cause that object to move, to accelerate, in the direction of the larger force. So we can actually see this here in this picture. Okay, I have one force acting in this direction, another force acting in this direction, so the net force is this. If I take this force in this direction and subtract this force coming back, my net force is this much and going to the left. When I have equal and opposite forces, they total up, as we know, to be 0. Those are balanced. A and B are unbalanced. Now that we know what forces are, we can actually apply these using force and motion and connect them using Newton's laws of motion. So what we're going to do is we're going to look at Newton's first law here. This is also called the law of inertia. Inertia is basically the tendency of any object to resist a change in its motion. And how we tie this into force is if an object has a balanced force acting on it, its state will not change. So in other words, if it's moving, it's going to stay moving. If it's not moving, it's going to stay not moving if a balanced force acts upon it. We often hear Newton's first law stated something along these lines. An object at rest stays at rest. An object in motion stays in motion in a straight line and at the same speed unless acted on by an outside force. So that's all well and good, and that may be something you may have memorized in middle school, but what does that really mean? That's what we really need to look at. Well, what Newton's first law is telling us is objects don't want to change what they are doing. If they're moving, they want to stay moving. If they're not moving, they want to stay not moving. They don't want to speed up. They don't want to slow down. They don't want to turn, because remember, when they turn, they accelerate. Okay, so basically they don't want to accelerate in any way, shape, or form. Now let's look at a practical application of this here with these pictures. These are from a car crash test. Okay, so if you look here, we have forces that are acting. There's the force of the car going forward, and then there's the force of the wall coming back at the car. Those forces act upon you within the car when you're in a car accident. Okay, the car doesn't want to change its motion. It wants to keep moving in that straight line. The wall doesn't want to change its motion either. It wants to keep moving or keep at rest and push back this way. Obviously, those are at odds with each other when they come in contact. And this is the idea behind a car accident. Car accidents and car manufacturers, they have to manufacture their cars in such a way that those forces upon these impacts don't affect us in such a way that it does not allow us to survive. Those forces can actually cause us very serious injury or harm when we're in a car accident. An object's resistance to change in motion is called its inertia, and it is directly related to the mass of the object. So the idea here is that the higher the mass we have, the greater the inertia. So if we have more mass, we're going to get more inertia and more resistance to our change in our motion. So let's wrap up this section here, introducing force and Newton's first law, by reviewing our big ideas. All right, how does a net force, zero net force, affect an object's motion? Well, when we have a zero net force, our motion does not change. Okay, if we think back to our car crash, which objects and devices are going to help absorb the energy of the crash and disperse the forces? Well, as you saw, that is all of the above. The crushing of the car's body actually changes the angles that the force happens, so it actually pushes the force outward so it doesn't impact us directly. The airbag and the seat belts actually help to prevent us from continuing our forward motion. Because that would actually hurt us a lot if we continued into the steering wheel. All right, these are some other questions to think about. What is the effect of inertia on the car and on the dummy in the figure? Well, the car doesn't want to change its inertia. It doesn't want to change its motion. It wants to keep moving. But remember, the dummy that's in the car also doesn't want to change its inertia. So when the car stops, the dummy wants to keep moving. How is the mass of the passenger related to the passenger's inertia? Basically, the higher the passenger's inertia, the higher the passenger's mass, the higher the inertia. So people who are larger actually have a harder time in some of these car accidents simply because those objects and devices that we have to stop larger forces in the direction of motion. What would happen to the dummy if the airbag did not deploy and the dummy was not wearing a seatbelt? Well, there would be less chance of them stopping their motion in a safe manner, basically. All right, so that wraps up the idea behind force and Newton's first law. And what we will do is in the next section, in the next lesson, we will actually talk about Newton's second law of motion.